So in particular, right, if you have a time-invariant system, you can write h sub tau of t as, so this is the response to an impulse at time tau, right? You can write this response as a time-shifted version of the response that you would get for an impulse at time 0. Okay, and we call this the unit impulse response, similar to that in the discrete time case. So now if you take this and plug it into this integral here, then what you get is the integral of x of tau, h of t minus tau d tau, and we call this the convolutional integral or the superposition integral. Okay, now you can also denote this as x of t star h of t, which is the notation for the convolution between two functions x of t and h of t.
Okay.
那所以你了解说为什么 h sub tau of t 这个 h sub tau of t 可以写成 h of t 减 tau 吗？
对，因为它是 time-invariant system。
对，所以说 h of t 假设是这个时间零来的这个 delta function 的话，那么如果你delay 时间 tau 才进来的话，那它对应的 response 就会是这个 h of t delay 同样的这个时间。
对。
OK， 对 ，OK， 好，谢谢。那周玉成
在。
有没有什么问题？
那个老师可以再讲一下，就是第16，就上一页。
上一页 ，OK。
对，就是可以讲一下下面那个图为什么会长那样。
你说这个图吗？
对。
OK， 所以这个图的这条线是假设是 x of tau h sub tau of t 这个 function，OK， 那这个 x of k delta h sub k delta of t， 这个就是我这个 function sample 在 tau 等于 k delta 的这一点的值，就是这一点的值，这可以理解吗？
可以。
对，就是这一点的值，就是这个 xk delta hk delta t。那所以说，它这个 rectangle 底下的 area 就会是这个高度乘上它的 interval 的长度 delta。OK， 那所以说我如果对每一个这个 integer k delta 都做这件事情的话，我是不是可以得到一个 function 是跟这一条线很像的？
对。
对，那我如果去加起来这些的 area 的话，就会是在 delta 趋近于0的时候，就会趋近于这个 function 的积分，就是它底下的 area。OK，
懂。
OK， 所以这个应该就是那个黎曼积分的一个概念，这样子。
谢谢老师。
好，谢谢。好，还有没有其他的问题？ So if not, let's continue with an example. Okay. All right. So basically, right, similar to the discrete time case, this convolutional integral or the superposition integral can be viewed in two ways, right? One is to view it as a superposition of impulse responses, right? So we're viewing this as a superposition of impulse responses, responses to different impulses arriving at separate times, okay? Or if we want to look at the output at a particular time instant t, then we can also view this as summing the contribution of x at different times, okay? Summing the contribution of x at different times on the response at time t, okay? So we can also view this as the sum or the integral of contributions of x tau to the output at time t, okay? All right, so this is basically done by computing this convolution between x of t and h of t. Okay. So let's consider an LTI system with input x of t equal to e to the minus at times a unit step function for a greater than 0. So your x of t will look something like this. That is non-zero only for positive tau. And you have a function that starts from 1 and decays over time, right? And suppose that the system is characterized by this impulse response that is equal to a unit step function, right? So to compute the output, you need to take, right? So to compute the output, you need to compute the convolution. So basically, you need to first find a time-reversed function of h shifted to time t. Okay. So here is your function h. Right. Now suppose you want to find h of t minus tau. You first want to, take its time-reversed version so that it's reflected about the origin, and then shift this function to t, okay? So suppose that t is negative somewhere here, then what you have is this function here, okay? So for t less than 0, you can see that x tau, h of t minus tau, right? These two functions have no overlap, so the multiplication is equal to 0 for all tau, and therefore y of t is 0. Okay? Now, for t greater than 0, right? So for t greater than 0, meaning that you're moving this to the positive time, right? So that you have partial overlap with x. In this case, x of tau, h of t minus tau will be equal to e to the minus a tau for tau between 0 and t and 0 otherwise. Okay, so if you take the integral of this, right, you have the integral of e to the minus a tau from 0 to t d tau, and this gives you 1 over a 1 minus e to the minus a t. Okay, so in summary, what you have, okay, at the output, this y of t is a function that is 0. Is a function that is 0 for time t less than 0. And then increases as time t increases, right? So as time t goes to infinity, this becomes 0. So the maximum value is 1 over a. Right, so you gradually increase to this. Now let's look at another example. Okay, so here we have x of t that is equal to 1 from 0 to capital T. So this looks something like this. Okay, so from 0 to capital T. Okay, so from 0 to capital T, the magnitude is 1, and it's 0 everywhere else, right? And for h of t, it looks something like this. It extends to 2t, right, and increases from 0 to 2t, and everywhere else is 0. Okay. Now, you want to compute the convolution of this, so you first take the time-reversed version of h and slide it through your input signal x. Okay. So suppose that you're first looking at the case where t is less than 0, right? So in this case, your signal x of t will be somewhere around here, right? Somewhere around here. Okay. And you see that there's no overlap between the two. So x tau h of t minus tau is equal to 0 for all tau, and therefore y of t is equal to 0 in this case. Okay. Now, if you start to move this t to the right, suppose t now is between 0 and capital T, right, so that it overlaps partially with the input signal, okay, then x of tau, h of t minus tau will be equal to t minus tau for tau between 0 up to t, right, 0 up to t, and 0 otherwise. Okay? And therefore, if you integrate this, you get y of t, which is the integral from 0 to t, t minus tau, d tau. And this is equal to t squared over 2. Okay? So it's basically the integral of this triangle here. Right. Now, if you move further along, then this will completely overlap with the input function. Okay, so you have x of tau, h of t minus tau, that is equal to t minus tau for tau between 0 and capital T and 0 otherwise. Okay, so if you integrate over this, you get y of t. Okay, so I'm omitting the derivations here, but you get y of t equal to t capital T minus t squared over 2. Okay. Now you can continue to do this, right, to move this triangle towards the right. Right, so suppose you have t falling between 2 capital T and 3 capital T. So this means that you're again covering the input signal partially, right? So in this case, if you compute the okay, let me Okay, let me write this out again. You have t minus tau, but for tau between t minus 2t to capital T, right? So this point here is t minus 2t, okay, up to capital T, okay, and 0 otherwise, okay. So if you integrate this, you get yt equal to minus 1/2 t squared plus t times capital T plus 3/2 capital T squared. Okay. Now, as you move t beyond 3 capital T, then they no longer overlap, right? The input signal and h no longer overlaps, and therefore y of t is 0. So if you summarize what you get, if you summarize what you get here, right? You have y of t equal to 0 for t less than 0, t squared over 2 for t between 0 and capital T. You get this for capital T to 2t. You get this for 2t to 3t, and 0 again for t greater than 3t. Okay? So if you plot it out, you will get something like this. You can see that for t less than 0, it's first 0. Then from 0 to capital T, it increases quadratically, right, up to this point. Then from capital T to 2t, it increases linearly up to this point. And then for 2t to 3 capital T, right, it then decreases quadratically to 3t, and then 0 afterwards. So you can see that the relationship here is, quadratic, whereas the relationship in this region is linear, okay, and so on.